The explanation for the special stability of aromaticity is probably best explained through molecular orbital theory, which I have referred to briefly in other instances. It's quite complicated, so we typically only touch on it briefly in organic chemistry at this level. But essentially, the idea behind molecular orbital theory is that individual atomic orbitals add together to form molecular orbitals. So molecular orbitals belong to the entire molecule, whereas atomic orbitals belong to an atom. And in this idea, we would take, for example, with benzene, the 6 p orbitals. So each carbon in benzene is sp2 hybridized and has a p orbital. We would add up all of those p orbitals together, and we would get out molecular orbitals. And there's a rule with orbital addition, and that's that the number of orbitals you add together must equal the number of new orbitals that you produce. So since we're adding 6 p orbitals, we're going to get 6 molecular orbitals out. So what I want you to take away from this slide is just that you get molecular orbitals that are lower in energy than the starting atomic orbitals, and that each of these molecular orbitals is going to contain 2 pi electrons. And as a result of this, there is a net stabilization effect when you have aromatic compounds, and that is the source of the stability. Now with anti-aromaticity, so for example, if you had 8 pi electrons with 8 p orbitals, you end up with molecular orbitals that contain unpaired electrons, which is not stable. So that's why with certain compounds that have 4 n pi electrons, you get this special instability, and that's called anti-aromatic. So what have we learned so far? We've learned that aromatic compounds are unusually stable. Anti-aromatic compounds are unusually unstable. The reason for this is explained by molecular orbital theory, which we just touch upon in this class. There are criteria for determining if a compound is aromatic or anti-aromatic. You have to be planar and a conjugated monocycle. And then if that first condition is met, you count up the pi electrons. And if the pi electrons equal the formula 4n plus 2, you're aromatic. If they meet the formula 4n, you're anti-aromatic. If that first condition isn't met, your compound's just your typical average non-aromatic compound. Nothing special about it. Now, technically, Huckel's rule is only relevant to monocyclic compounds. However, the concept of aromaticity can be applied to polycyclic aromatic compounds. So when looking at these are all aromatic compounds. So naphthalene has 2 rings, anthracene has 3, benzopyrene has 5, and so forth. You still apply the rest of the criteria the same. So it's more than 1 ring, but every carbon is sp2 hybridized, so it's conjugated. And then when you add up the pi electrons, they're going to equal the formula 4n plus 2. So with naphthalene, for example, that also exhibits resonance. There are more resonance forms, and these compounds are especially stable because of their aromaticity. And this is just an orbital view. If we draw in the p orbitals of naphthalene, we see that there's a continuous array of p orbitals. The final topic in this video is aromatic ion. So an ion is a charged molecule, either positively or negatively. So aromatic rings can contain carbanions or carbocations. Remember that carbocation carbons are always sp2 hybridized. Carbanions, you have been taught, are sp3 hybridized, but we'll see in a second it actually depends. So let's first look at this example. Is this ring aromatic? So let's look at our criteria. Is it a ring? Yes. Is it planar? We're going to assume it's planar if it's conjugated, unless I've told you otherwise. So then the real question, is it conjugated? Is every carbon sp2 hybridized? So these carbons are sp2 hybridized, and I just mentioned here that carbocation carbons are always sp2 hybridized. So yes, it's conjugated. So it fits criteria number 1. So then we're going to add up the pi electrons. There's 2 in that double bond. Now the carbocation carbon has a p orbital, but it's empty. So there are no pi electrons contributed from that carbon. So there's only 2 pi electrons. But that does meet the Huckel's rule if n is equal to 0. So yes, this is aromatic. Now what about negatively charged carbons? So this is the tricky part, because carbanion carbons, while they are typically sp3 hybridized, they will become sp2 hybridized if that then makes the compound aromatic. So the rule is that the carbon with a negative charge will only be sp2 hybridized if by doing so the whole compound is aromatic. Otherwise it's sp3 hybridized. So let's take a look at whether or not that's aromatic. So is it a ring? Yes. Is it planar? We assume so if it's conjugated, and I haven't told you otherwise. So then the next question is everything sp2? Well, let's go ahead and make it sp2. So if this is sp2, then that would make all of the carbons sp2, and it would be conjugated. So criteria number 1 would be met. So then we count up the pi electrons. So here's a picture of what it looks like. So each double bond has 2 pi electrons, and then when we have a carbanion, if it's sp2 hybridized, that lone pair, that's the source of the negative charge, is in a p orbital. So that's going to also contribute to the number of pi electrons. So the total pi electrons would be 6 pi electrons, which equals the 4n plus 2 rule. So this would be aromatic. So notice here there is a little bit of trial and error in looking at carbanions, because we first made the assumption that this carbanion was sp2 hybridized. And then we continued on to see if by making it sp2 hybridized, did it make the whole thing aromatic. In this case, it did. Therefore, we were right to assume it was sp2 hybridized. If, however, we had gone through the logic of this process and we had reached an answer that it was anti-aromatic, then it would not be sp2 hybridized. The true reality would be sp3 hybridized. Okay, now which of these structures is aromatic, anti-aromatic, or non-aromatic? So let's start with the top structure here. So here we have a ring, but is it conjugated? So this carbon's sp2, as is this one and this one and this one, and I said the positive charges, those carbocations are always sp2. But what about this last carbon? That's sp3. It has 4 bonds attached, 2 to carbons and 2 to hydrogens. There's no way that can be sp2. So this fails criteria number 1. So it's just simply non-aromatic. Now what about this next example? So all of the atoms are sp2, so it's conjugated, it's a ring. We assume it's planar if it's conjugated unless I told you otherwise. So everything is conjugated, so it satisfies criteria number 1. Now we move along to add up the pi electrons. 2 from each pi bond equals 4. The positively charged carbon contributes nothing to that count. So 4 is equal to 4n, where n is 1. So that would be the anti-aromatic number of pi electrons. So that compound's especially unstable. Now what about the next compound? So this one, all of the atoms are sp2 hybridized. So it satisfies criteria 1. It's conjugated, it's a ring. We assume it's planar. And then we count up the pi electrons. There's 6. We know 6 meets Huckel's rule, where n is 1. So this one is aromatic. And then this last one I just did for you on the last slide, and we decide that one was aromatic as well. The final topic is heteroaromatics, and those are just aromatic rings that contain atoms other than carbon or hydrogen. And for example, pyridine looks a lot like benzene, but it has a nitrogen in it, as does pyrrole. And these are both aromatic compounds. Even if the heteroatom is not part of a double bond, it will still be sp2 hybridized if that makes the compound aromatic. If the heteroatom's lone pair is necessary for aromaticity, it will be included in the Huckel number of pi electrons. So let's analyze why pyridine and pyrrole are aromatic. Pyridine is probably the easier one to look at. So that nitrogen has a lone pair, and this would be an orbital drawing of it. So every atom in the ring is sp2 hybridized, so therefore it's conjugated. It's planar, we assume if it's conjugated it's planar unless I've told you otherwise. It is a ring, so criteria number 1 is satisfied. Then we move on to counting the pi electrons. This is where people can get confused because you need to know what orbital is the lone pair in. Well, the nitrogen is participating in a double bond with a carbon next to it. So that double bond is consisting of 2 overlapping p orbitals. That means that the lone pair has to be an sp2 hybridized orbital that's 90 degrees away from the p orbitals. So the lone pair is not included in the pi count because only electrons in p orbitals count towards the pi system. So that means we've got 2, 4, 6 pi electrons from each double bond, not the lone pair, because it's in an sp2 orbital. And that equals Huckel's rule. It fits Huckel's rule, so that's aromatic. Now let's look at pyrrole. Now there's a lone pair on the nitrogen. This one's more confusing. So here we have to decide, is that nitrogen going to be sp2 or sp3 hybridized? So just like with the carbanions, let's start with thinking it is sp2 hybridized. If it's sp2, then criteria number 1's met because it's conjugated, it's planar, it's a ring. Then we really need to look at an orbital description to understand where all the electrons are. So the double bonds between carbons are formed from overlapping p orbitals. So there's 2 electrons from each double bond. But then where is that lone pair? Well, that lone pair is going to be in a p orbital, because if it's sp2 hybridized, the 3 sp2 hybrid orbitals have to be involved in the formation of sigma bonds. And the nitrogen has 3 sigma bonds. So that takes care of all 3 available sp2 hybrid orbitals, leaving only a p orbital to place the lone pair. Now that the lone pair is in the p orbital, it does count towards the pi electron total. So now we have 2 from each double bond, plus the 2 in the lone pair, for a total of 6. So now that satisfies Huckel's rule, and this is also aromatic. Okay, now I want you to test your knowledge. So I'm going to draw 4 compounds, and then in the chat I want you to determine if these are aromatic, anti-aromatic, or non-aromatic. So the first one, called cyclobutadiene. It's a 4-membered ring with 2 double bonds. Here's your next one. Here is another one. And finally, this compound. It may help you here to draw in your lone pair electrons that aren't shown. So your heteroatoms, your oxygens, your sulfurs, they have lone pairs, but they're typically not drawn in. So analyze all 4 of these, and then in the chat indicate if you think they are aromatic, non-aromatic, or anti-aromatic. And that's all for this video.